Good morning, everyone. Myself Darshan BD, Assistant Professor, Department of ECE, SJBIT. So today we are discussing the Module 2 topics on Introduction to Electronics and Communication Engineering. Here in the Module 2, so today we are going to discuss the crystal controlled oscillators, then some topics in operational amplifiers. Consider the crystal controlled oscillator. A crystal oscillator generates electrical oscillations of constant frequency based on piezoelectric property of the crystal. A requirement of some oscillators is that they accurately maintain and exact the frequency of oscillations. So in such cases, a quartz crystal can be used as a frequency determining element. The quartz crystal, a thin slice of quartz in a hermetically sealed enclosed, you can observe in the figure, vibrates whenever a potential difference is applied across its faces. This phenomenon is called as the piezoelectric effect. The frequency of oscillation is exactly equal to the resonant frequency of the crystal. The piezoelectric effect is an effect in which when voltage source is applied across it, it will change shape and produce mechanical forces, and the mechanical forces revert back and produce electrical charge. You can observe here the frequency of oscillation is determined by the crystal's cut and physical size. Most quartz crystal can be expected to stabilize the frequency of oscillation of circuit to within a few parts in a million. Crystals can be manufactured for operation in the fundamental mode over the frequency range extending from 100 kHz to around 20 MHz, and for overtone operation from 20 MHz to well over 100 MHz also. So you can observe here we are having two figures. So the figure 1 shows the quartz crystal. So figure 2 shows the simple JFET oscillator. So when you are going to consider the crystal, so how we are going to generate that the oscillation? This crystal is generating the fixed oscillations. Consider when AC voltage is applied across the crystal, it starts vibrating in a resonant frequency and it looks like an equivalent tuned circuit. When the crystal mounted across the AC source, and if it is not vibrating, it is equivalent to capacitance. When it vibrates, acts like a tuned RLC circuit. In crystal oscillator, R denotes the initial frictional losses, L denotes the mass of the crystal, and its stiffness represented by a capacitor C. Because capacitor, the crystal has two resonant frequencies, serial resonant frequency RLC determine the resonant frequency. The crystal has low impedance at which 2 pi FL is equal to 1 by 2 pi FC. Second, the resonant frequency is the parallel resonant frequency. So RLC and the capacitor CM determines this resonant frequency. The crystal has high impedance at which the parallel resonant frequency RLC and CM determines the resonant frequency. The crystal has high impedance at which 2 pi FL is not equal to 1 by 2 pi FC. The series and parallel resonant frequencies are very close. We can consider this. So the crystal oscillators gives the constant frequency based on the which crystal we are going to use. Consider some example. Determine the frequency of oscillation of 3-stage ladder network oscillator in which C is equal to 10 nanofarad and R is 10 kilo ohm. So consider this and we are going to substitute this in the value f is equal to 1 by 2 pi root 6 into RC, and we are going to substitute these values. Frequencies 647 Hz. This is 3-stage ladder network oscillator. This is the example for the Wien bridge oscillator based on an operational amplifier. So here we are going to consider C1 is equal to C2. Then, so we are considering the two cases. So considering the two cases, we are going to solve using the formula f is equal to 1 by 2 pi CR. Using this, we can find out the frequency. For first case, we are going to get frequency is 1.59 kilohertz. For the second case, means R1 is equal to R2 is 6 kilo ohm. The frequency of oscillation is 265 Hz. So from these problems, we can come to know that resistance and capacitance values will main the component in varying the frequency. Then by varying the resistance, we can control the frequencies. Next, move on to the operational amplifiers. As we all know that the operational amplifiers, the integrated circuit operational amplifier called as OPAMP is the fundamental building blocks for many electronic circuits. An operational amplifier is a multi-stage, direct coupled, high gain, negative feedback amplifier used to amplify AC and DC input signals. The main applications of OPAMPs is we can use as active filters, we can use as oscillator, we can use as peak detector, we can use as a comparator, voltage regulator, precision rectifiers, instrumentation and control system, pulse generator, square wave generators. So we are having enormous applications considering the operational amplifier. Consider the operational amplifier, the circuit symbol. So you can observe here, this is the circuit symbol. In this, actually the operational amplifier, so we are going to use A741 IC. The 741 IC is a 8-pin IC. Actually, so this inverting input is the pin number 2, non-inverting input is pin number 3, output is pin number 6. So positive supply is pin number 7, negative supply is pin number 4. So totally 5 pins we are going to use. Then pin number 1 we are going to use as a offset null. Then pin number 5 is also offset null. Then pin number 8 we are not going to use. Out of 8 pin, mainly we are going to use this 5 pin for our use. So in this circuit symbol, so considering this operational amplifier having two inputs, inverting input and non-inverting input, one output. Inverting input is applied to negative symbol, non-inverting is applied to the positive symbol. So then two supplies, positive supply and negative supply. So we can consider that plus VCC and minus VCC. So up to 6 volts to up to 15 volts we can apply. Output is non-inverting input minus inverting input, that is output. So they divide as two inputs and one output, no common connections. You can consider here the input is marked negative and other input is marked as positive. The positive sign indicates 0 phase shift, the negative sign indicates 180 degree phase shift. Since 180 degree phase shift is produced in an inverting waveform, the negative input often referred as a inverting input. The positive input is referred as non-inverting input. Most operational amplifier requires a symmetrical supply. So consider that up to maximum 6 plus or minus 6 volts to plus or minus 15 volts we can apply for positive supply to negative supply. which allows the output voltage to swing from both positive and negative. Consider this. This is the internal structure of this operational amplifier. It shows how the supply connections would appear if we decided to indicate them. So note that we usually have two separate supplies, positive supply and an equal but opposite negative supply. The common connection to these two supplies is 0 volts. That is connected as supply connection, 0 volt supply connection acts as a common rail in our circuit. The input and output voltages are usually measured related to this rail, means related to this the common voltage, that you can call it as 0 voltage. Consider the operational amplifier parameters. Coming to this operational amplifier parameter, considering open loop voltage gain, closed loop voltage gain, input resistance, output resistance, input offset voltage, bandwidth and slew rate. So these are the 7 operational amplifier parameters we are going to consider. So from this, we are going to detail, we are going to discuss in each parameter. So in the operational amplifier parameter, first one we are considering open loop voltage gain. So what is the open loop voltage gain? The open loop voltage gain of an operational amplifier defined as ratio of output voltage to input voltage measured with no feedback applied. The term indicates that open loop voltage gain. So in that time, so we should consider that the feedback, no feedback applied. So in practice, this value exponentially high, so typically greater than 1 lakh, but it is liable to considerable variation from one device to another device. Open loop voltage gain may thus be brought off as the internal voltage gain of the device. Consider AV. In bracket we are considering OL, means open loop, is output by input. The open loop voltage gain is often expressed in the decibel, so rather than is a ratio, so that you can consider 20 log base 10 of V out by V in. Consider that AVOL is the open loop voltage gain, V out and V in are the output and input voltages respectively under open loop condition. Most operational amplifiers have open loop voltage gain of 90 decibels or more. The next one is closed loop voltage gain. The closed loop voltage gain of an operational amplifier is defined as ratio of output voltage to input voltage measured with some small, the portion of the output is fed back to the input. It is called the feedback. So we are considering the closed loop voltage gain with feedback. The effect of providing negative feedback is to reduce the loop voltage gain to a voltage that is both predictable and manageable. The practical closed loop voltage gain range from 1 to several thousands, but note that the high values of voltage gain may make unacceptable restriction on bandwidth. We can consider that. So AVCL means closed loop is V out by V in. You can consider open loop voltage gain, the output and input voltages under closed loop condition. The closed loop voltage gain is normally very less than the open loop voltage gain. So always closed loop voltage gain is less than the open loop voltage gain. Consider an example. An operational amplifier operates with a negative feedback, produces an output voltage 2 volts when supplied with an input of 400 microvolts. Determine the closed loop voltage gain. So we know that closed loop or open loop voltage gain. So that output by input. So you can consider that. So output is 2, input is 400 microvolt, micro is 10 power minus 6. So 2 into 10 power 6 divided by 400, we are going to get the voltage gain is 5000. So we are going to express this, the voltage gain in decibel, so rather than the ratio, so that we have to use the formula. So 20 log based in of, so V out by V in. So can consider 20 log based in of 5000, we are going to get the 74 decibels of open closed loop voltage gain. Next parameter is input resistance. The input resistance of an operational amplifier is defined as ratio of input voltage to the input current expressed in ohms. So we can determine that the input resistance is a ratio of input voltage to input resistance. Rin is equal to V in divided by I in. So you know that the Ohm's law formula, V is directly proportional to I. So considering that, so V is equal to I into R. With that, R is equal to V by I. So with respect to that input resistance, we are going to consider input ratio of input voltage to input the current. Considering output resistance, the output resistance of an operational amplifier is defined as the ratio of open circuit output voltage to short circuit output current. Expressed in ohms, output resistance is the ratio of open circuit output voltage to short circuit output current. So you can write that equation, R out is equal to V out by I out. So output voltage considering the open circuit, then current we are going to consider as a short circuit. Next parameter is input offset voltage. So what is input offset voltage? So an ideal operational amplifier should provide zero output voltage when 0 volt difference is applied to its input. And I am going to consider both inputs are 0 or both inputs are equal. Okay, so output is 0 because output is V2 by minus V1. Because we are going to take the two input differences at the output point. The voltage that must be applied differentially to the operational amplifier input in order to make the output voltage exact 0 is known as the input offset voltage. Okay, in some cases the output is not exactly equal to 0, so due to some internal leakage, so in that time, so we have to give some external voltage to make that output voltage 0. So that voltage we are going to call it as input offset voltage. Input offset voltage may be minimized by applying the relatively large amount of negative feedback by using the offset null facility provided by a number of operational amplifier devices. So typical values of input offset voltage range from 1 millivolt to 15 millivolt. Next is full power bandwidth. Full power bandwidth of an operational amplifier is equivalent to the frequency at which the maximum undistorted peak output voltage swing falls to the 0.707 of its low frequency DC value. Typical full power bandwidth range from 10 kilohertz to over 1 megahertz for some high speed devices. Slew rate. Slew rate is the rate of change of output voltage with the time when a rectangular step input voltage is applied. Slew rate, you can consider that the equation slew rate is the delta V out by delta T. Delta V out is the change in the output voltage and delta T is corresponds to the interval of time, so that is in seconds. Slew rate is measured in V by second volt per second, and typical values range from 0.2 volts per second to 20 volts per microsecond. So consider an example, an operational amplifier has an input resistance of 2 mega ohm. Determine the input current when an input voltage of 5 millivolt is present. So that Rin is V in by I in. So can find out the I in current V in by R in. so that we can get the input current is 2.5 nano ampere. This is also example. So the perfect rectangular pulse is applied to the input of operational amplifier. It takes 4 microseconds for the output voltage to change from 5 volts to minus 5 volts to 10 plus 5 volts. Determine the slew rate. So this slew rate is rate of change of V out by time. Okay, so now delta V out by delta T. So delta V out is change from minus volts to minus 5 volts to plus 5 volts, so that we can totally consider 10 volts. So time is 4 microsecond, so that the slew rate is 2.5 volts per microsecond. This is another example. So to find out the when you are going to consider a slew rate, says slew rate is given 15 volts per microsecond and output voltage is given so 2 volts. So what is the time, rate of change of time, that so that you can write the delta T is, we can rearrange the formula. Delta T is delta V out by slew rate, so 2 volt by 15 volts per microsecond, so that we can write 2 by 15 0.133 to microsecond. Thank you.